Welcome to our explainer, where we break down big topics into something you can really wrap your head around. Today, we're jumping into the world of solutions, and trust me, it's the invisible chemistry that is absolutely everywhere.
So let's kick things off with a bit of a riddle. Think about a can of soda, a gold ring on your finger, and the very air you're breathing right now. I mean, they couldn't be more different, right? But what if I told you they all share a fundamental chemical secret?
The answer, believe it or not, is that they are all chemical solutions. It's one of those ideas in chemistry that once you get it, you start seeing it absolutely everywhere you look.
Okay, so to really understand that, we have to go back to basics. We have to ask, what is a solution anyway? Now, in everyday life, a solution is just an answer to a problem. But in chemistry, it means something way more specific.
A solution is just a perfectly uniform mixture, homogeneous. Think about it. When you stir salt into water, the grains just disappear, right? The mix is totally even. Now, for what we're doing today, we're going to keep it simple and stick to what are called binary solutions, which just means they've got two parts.
And those two parts have names. The thing you have less of, the stuff getting dissolved, that's called the solute. And the thing you have more of, the stuff doing the dissolving, that's the solvent. Simple as that.
But here's the thing. When you hear solution, you probably picture a solid dissolving in a liquid. But that is just scratching the surface. It's only one of 9 different possibilities. Let's take a look at the whole picture. So, if you take the 3 states of matter, solid, liquid, and gas, and mix and match them as both the solute and the solvent, you end up with 9 totally distinct types of solutions. And this takes us right back to our riddle from the start. That gold ring? That's actually a solid dissolved in another solid. We call it an alloy. Your soda? That's a gas dissolved in a liquid. And the air we're all breathing? That's a solution of different gases all mixed together. See? It's everywhere.
Okay, so knowing the different types is one thing. But for a chemist, that's not enough. They need to know how much solute is actually in there. Is your coffee weak or strong? That's where the idea of concentration comes in. Concentration is what it's all about. It's the measurement that lets us be precise. It turns a vague description like salty water into a hard number, a value that tells us the exact ratio of the stuff dissolved to the stuff doing the dissolving.
Now, when you start measuring concentration, there's one really important catch you got to be aware of. If your measurement is based on volume, like liters, it can actually change with the temperature because, liquids expand when they get hot. But if your measurement is based on mass, like kilograms, it's solid. It won't change no matter how hot or cold it gets. And a perfect example of this is the difference between molarity and molality. I know they sound almost the same, but they are fundamentally different. Take a look at the definitions. Molarity is about the volume of the entire solution. Molality is about the mass of just the solvent. It seems like a tiny difference, but believe me, it has huge implications in the lab. Okay, now we're getting to what I think is the most fascinating part of all of this. This is where the actual identity of a particle stops mattering, and all that matters is that it's there. This is where solutions start to do some really weird and powerful things.
Think of it like this. Some things are all about the size of the crowd, not about who is actually in the crowd. It doesn't matter if you have 100 celebrities or 100 regular folks in a room. Either way, the room is still just as crowded.
In chemistry, these crowd-based effects are called colligative properties. And here's the key takeaway. They depend only on the number of particles you've dissolved, not on what those particles actually are. It is all about quantity over quality.
And there are 4 main colligative properties you need to know about. They are behind everything from the antifreeze in your car to how plants are able to drink water.
First up, you've got the lowering of vapor pressure. Basically, adding stuff makes a liquid harder to evaporate. Second, the boiling point goes up. That's why you add salt to pasta water. It makes it boil at a hotter temperature. Third is the exact opposite. The freezing point goes down. That's why we salt the roads in winter. It helps melt the ice. And finally, you have osmotic pressure, which is this incredible force that drives water across membranes. It's fundamental to life itself.
So, these rules seem pretty straightforward, right? But what happens when our predictions based on these rules just fail? What happens when we think we know how big the crowd is, but the results just don't add up?
Well, here's a great example. Let's say you dissolve 1 mole of sugar in water and 1 mole of table salt in the same amount of water. You'd expect them to have the same effect on those colligative properties, right? I mean, it's 1 mole of each.
But in the real world, the salt has a way bigger impact. So why? The secret is in something called dissociation. See, a sugar molecule dissolves, but it stays as one single particle. So 1 mole of sugar gives you 1 mole of particles. But salt, NaCl, is different. When it dissolves, it splits apart into 2 separate ions, a sodium ion and a chloride ion. So for every 1 unit of salt you add, you actually get 2 particles in the solution. It doubles the crowd.
So to fix our math for this weird behavior, scientists came up with a clever little tool. It's called the Van't Hoff factor, and it's represented by the letter I. You can think of it as a correction factor, a simple multiplier that accounts for whether particles split up, or sometimes even clump together when you dissolve them.
So really, the most important point to take away from all this is simple. In the world of solutions, it's not just about what you're adding, it's about how many effective particles it becomes once it's in there. The final head count, that's everything. And that really leaves us with a final thought to chew on. If the number of particles is what truly matters, how does that change the way we look at the world? From the antifreeze protecting an engine block to the incredible pressures at work inside our very own cells, it kind of shows that often, in science, the most powerful force isn't the individual, it's the crowd.